Welcome the only lady in the building, Sandra Kuma, who is my boss. How are you doing? Sandra is the Sandra is a very brilliant student. If you don't know, very sharp from UNE.
Please, I'm fine by God's grace. Please yourself.
I'm also very fine.
I'm glad to hear.
Yeah. So guys, if you have any problems, academically, Sandra is there to help you. She is very brilliant. She's unlike us, and she is serious in life too. So you can reach out. She'll help you. Maybe charge you something small. You'll be good to go. Yeah. So that's it. Don't mind whatever she says. She go explain to you, no evidence, right? So guys, let me just share my screen and see what we have. Okay, so we have 1 minute more, but let me just scroll up to the very first. So this is what we're going to look into from here. We're going to look into some of these things. Um, Today it's going to be very detailed. But most of them we've already done them. I'm not going to the EDA and all those ones. I'm not going to talk about all these guys again. We've done them already. So we're just going to skim through and then we go. So maybe this one is you can see I wrote some stuff here. I was when that was yesterday when I was there, it was like yo, let me just I was resting, I was like, oh, let me just try my hands on this thing we're doing. Let me rebrand it in a way so that more like make it more real and then write some inspirations and all those things that I don't know why I even wrote mission, vision and all those. But it's like I don't know. But I just don't know why I brought the write ups there. But maybe it was just a motivation for myself or something like that. But it's a good motivation. Now I put it there because some of us don't know the essence of why would you even build a stroke prediction model while there are doctors and all those ones. So you can see that according to WHO, stroke is the second killer disease of the world's total death, which is very weird. And then sorry, this disease contributes about 50% of total world death. And then this triggers my interest to do this project, something like that. I was like, when you do a project, you should know why are you even doing the project. And if me, who is not a data science person, I come to your GitHub, maybe Ripple or wherever, and I'm reading about the project, why should I even buy your idea? Why should I even see it to be interesting? Now you building, that is my motivation. I am building a stroke prediction model. Why am I why stroke prediction model? Because according to WHO, it is a second killer disease and then it kills but it contributes to over 50% or about 50% of the world's death. I'm a Muslim, I know that death is something you cannot, it's inevitable. More like if your time is due, you will die. But we don't want people to struggle that much before they die. If I'm dying at maybe age X, that is what God gave to me. I will definitely die at that age X. But what you have to know is that I can die healthy at that age X, or I can die, unhealthy at that age X. I can die whilst I'm maybe sick, or I can die whilst I am healthy. So it's up to me. If I don't take good care of myself, I may be sick. And if you look at the situation of Africa and Ghana, as, in particular, you can see that about almost over 80% of Ghanaians do not go to hospitals, and we are all victims of that. Most of us don't go to hospitals. We feel more like, oh, you know, Ebeko, we are ourselves self like there are a lot of doctors in Ghana. It's almost like everyone is a doctor in Ghana. You see me prescribing medicines and diagnosing myself and even friends and families. Your mother will look at you and be like, no, you have malaria. This one is this. Meanwhile, my mom, your mother and my mind and mine have never been to even, they've never even been to science lab before, but they would, I'm not saying sometimes they are right, but sometimes they are, most times they are wrong. So, and another thing is that because of that, this is leading to more like before somebody will go to hospital to kind of report stroke, you will see that the person would be hit by the wave before the person, before they report. The person will only go when he or she starts to suffer, maybe it's severely, you see one hand not functioning, or maybe one leg not functioning, or you see the mouth start to twist or something like that. Or maybe when he or she kind of faints and comes back, something like that. And which, according to doctors, do not help in treatment. When you discover something at the early stage, it is always easy to, you know, um, to treat than when you wait for it to grow very very distant. So that is me my motivation. I'm saying that okay, we're building this model. Let's just assume, and then it is very robust. We have a lot of data, real life data, and we build this model and we deploy it somewhere. You who has been to school can just say, okay, mom, you know what? There is this app we can just use to test your stroke probability or something like that, the probability of you getting stroke. So all you do is you go in there, you put your mommy's, health records, what it asks you, and then it tells you maybe your mother is 10% has 10% probability, or let's say 10% chance of you know having stroke. Then it will be very nice. So if you test and see that you have maybe, and we can even build on this, you know, kind of like upgrade it to where it will recommend things you do and all those things. So if, for example, I check and I have maybe 40%, then it means that I am almost getting stroke. So it will recommend probably go to hospital, do this exercise and all those things. Don't eat these foods, don't do these habits, do the do's and don'ts. And then I will know that no, I have to go to the hospital and I'll go, which is very nice thing. So that is my motivation. That is why I wrote that. And it's something personal I actually um, think of doing. And now, enough of the talk. Let's these ones you can read them on the history of the data sets, and then um, the mission and vision, blah blah blah. So now, enough of that. Let's come to the business of the day. Um, Today we're going to upgrade the um, model we've been working on, the classification model we've been working on, where the last time we looked at how to build a very basic logistic regression, which is a linear model, and then we saw that it wasn't really performing very well. So today we're going to upgrade it. We're going to look at ways to make way to actually improve the performance of a model, a logistic regression model, and not just that, other models as well. And then we're going to look at also on advanced ways, to build machine learning models, and ways to kind of like ease things for yourself and that. So if you look at the libraries we are importing here, we have few ones we are very, very familiar with. The top four, which is for pandas, that's our best friend. Pandas, we've always been using pandas for data wrangling, NumPy for numerical Python, all our numerical computations. We have Matplotlib and Seaborn for visualization. So we are cool with these guys. Now the new ones here are actually this guy, random forest classifier, and then but we know SKLearn, which is scikit-learn, machine learning, the only machine learning model we use in this course. The only machine learning actually not model but library. So we're saying that we are importing random forest classifier, which is also a model. We will talk more about what a random forest classifier is, but it is a classification model just like logistic regression. but that one is more robust and it is non-linear. We would learn more about that when we get to that session in this tutorial. But for now, you should know that we are actually um, importing it, and we are importing it from the ensemble, more like batch. So we saying that from sklearn dot ensemble, we are importing random forest classifier. Now, note that when we were importing logistic regression, we imported it from sklearn.linear models because it was a linear model. Logistic or random forest classifier um, it isn't a linear model, but it is actually an ensemble model, which you will know why it is an ensemble model very soon. And then another thing is we from the metrics we are not just going to use. We're going to upgrade the metrics we use. Over the course we've been using the very basic ones like accuracy. Now today we're going to import what we call confusion metrics display. We're going to use that. It is also a metric and you know what it is. So as usual, if you want to import any metric, that is any evaluator, anything, a metric is something we use to evaluate, the performance we use to measure the performance of a model. So as usual, you do from sklearn.metrics and we are importing confusion metrics display. And you will know what confusion metrics display is. Just it is don't be carried away by the name confusion, metrics. But you know why it is confusion metrics. Yeah. And then we are also going to import something which is we like I told you we will look at and then oh, calm down. So from model selection, we normally use to import train test split to split our data in training and testing. Now today we are adding another guy called gridsearch CV. Gridsearch CV is something we use to kind of fine tune or hyperparameterize models. So to find hyperparameters or tune hyperparameters or fine tune hyperparameters for models. And you know what a hyperparameter is. But now you know that this is how we import grid search CV. By the end of this, you will know what grid search CV is. Grid search CV is, yes. And then from sklearn.pipeline, we are importing make pipeline. Now, what make pipeline is just like when we say a pipeline, pipe, like a tube, a long tube. So from this end to this end, there is more like a lot of things. Water can pass through the pipe. Let's say if this is a pipe, from here to here, you know, water can flow through to any direction, maybe whether here or here. So in machine learning too, we can have like a pipeline where in the pipeline, in between the pipeline, from the start or from the start to the end of the pipeline, in between we will have a lot of activities going in there. So more like a process. So in the pipeline, maybe we can have three things happening, one after the other. So at stage one, we want you to maybe when the data enters, it should do this, then it goes to another session, it does this, and then it goes to the last session and it goes out. More like see it like a factory process, a process like kind of like a continuous process. Let's say maybe bread making, where we have like automated something. So the make pipeline is more like to automate something to automate processes in machine learning, and you will know how we do that very soon. And another thing is we also importing ordinal encoder. We've been ordinal encoder from sklearn pre-processing. Now the ordinal encoder, we all know what encoding is. That is transforming, features from one point or from one form to another. Now, um, sorry, my caption was on. So now we've been over the course. We've been manually doing the um, encoding where maybe we can say that one is for yes, zero is for no. Then we write codes to transform that and those things. Now today we're going to look at a way to do it, automatically. We don't have to do it manually, but we do it automatically for the machine learning model so that we don't worry so much about, you know, coming here, for example, gender, saying that okay, one for male, two for female, or maybe something like that. The machine learning model, everything will be automated, and then we just do it straight away. Yeah. So these are the guys we're going to, the libraries we're going to use today, and I'm very sure I've been able to explain it to you guys. So we're going to use the same stroke prediction model data set. So you can see it, you can see the one we used to build. We've been using this for a while, so I'm not going to talk much about it. So you can see it yourself. And then when we perform some validation techniques, we can see that it has 5,110 observations and 12 columns of features. And then um, this is the structure, and we can see that for the BMI we have some missing data, and that can be seen here. You can see that here we have NAN here, not a number here. So we will look at how to impute those ones and all those ones. So we also check, we do the validations and all those things. And let's come to the exploratory data analysis in here. We've done this already. So we look at, we visualize things to take a look into those guys in there, and we're not going to talk much about them. So now we're looking at correlation. Let's look at correlation between age and stroke. You can see that there is kind of weak correlation, positive correlation between age and stroke. Not that strong, maybe zero point 0.5 or, or about zero point 0.5, but it's still quite significant. Now we do visualize the other ones. I'm not going to talk about these guys because we've already done them, and we go straight to. So here we did some correlations. You can see that BMI and stroke do not have that much correlation, 0.04, which is almost no. And we do a value count of smoking status and all those guys. So we also visualize smoking status, and you can see that most of them never smoked, and formerly smoked follows in that order, like we did before. So if you don't understand this, you can go to your notebook in the logistic regression one, and then you can just visit them. And here you can see that we have what we call, this is stroke rate per smoking status. You can see that those who are formerly smoked have higher rate of getting stroke as compared to those who never smoked, and the others. Yeah. And then here we do a correlation check, and then we plot it using heat map, and you can see it's very nice. I'm not going to talk much about. I'm just skimming through these guys. But put in your head that um, BMI has some missing values, and here we're going to look at and the categorical. We kind of get the categorical, features, the features which have categories, and we kind of do more um, some analysis on it. What we did before, we've done all these guys in here. So and then we start to encode them. Now we're going to encode them. We're going to first encode them like the old one we did had in a manual way, like we did. Then when we finish, we look at how we can also um, do it in the automatic way I said. So in our usual way, we've encoded gender, and you can see that one for male, two for female, and we encode ever married, marriage status, one for yes, zero for no, and then the residential status, and then we come to type of work we do for smoking status, and then we can see we have them in here. Now let's split the data into training and testing into independent and dependent variable first. So as usual, big X for independent variables, and then Y for dependent variables. Here when you come, we drop in ID because in the formal this thing we said ID is just kind of like an ID for more like an index number for a patient. It doesn't really talk much about this patient's health status, just a number, so it wouldn't be necessary we use it in here. And then we stroke is actually the dependent variable, so we don't have to include it in the independent variables. Now we have encoded all these guys, so we don't need the unencoded ones, so that is why we drop in them too. And then the dependent variable is a stroke. Now we print or we output them, and you can see I've done something I have not maybe done before. I'm using just one print statement to print two things. So I'm first printing, I'm saying that like usual we do print. Um, so as usual I would have done maybe X shape, and I do this maybe, and I do X dot shape, and then that is going to let me kind of comment this out. And you see we have it. Now if you want to, you can just bring another print down here, and then like we normally do, and then do it for Y. Or you can do like I did here. So when you come here, you do another comma, and then you say um, I want to print Y shape. That is the next thing. And then just like we did, we just like repeating these guys here. And print will know that okay, we're saying that print another thing which is different from. So that one too is going to be shape. But you can see that they are on the same line. We want this one, the X one, to come on the next line. And that is what the backslash n. So backslash n is in Python is more like to tell Python that move the next thing, the thing which comes after backslash n to new line. So if you run this, you can see that now it comes to the next line. So whenever you want to move something to the next line, we use backslash n in Python. I think this is simple, self-explanatory. And then now, another thing we're going to do here is, here, before we always, whenever we have the data, we split it into X and Y, and we use all the independent variables to just predict, the dependent variable. But it is not always the case. You can have a lot of independent variables, all right, but most of them may not have so much power, or so much influence on the dependent variable. For example, we have a lot of independent variables in here like smoking status and all those guys, but it is not any independent variable which will have an effect on the person's stroke status. So to know the best way or the best practice in machine learning is to always use the independent variables which are significant or which are powerful in predicting the dependent variable. Again, it is not always the case that if you have maybe 11 independent variables and one dependent variable, it is not always the case that all the 11 independent variables will contribute to building or would affect the dependent variable. For example, if you have, for example, telephone number, let's say in the data you have telephone number or patient's number, which is a patient's phone number. In it, will you use the phone number to determine the person's true status? No. My phone number has nothing to do with my stroke status. Whether I use MTN or Vodafone, whether I use 05 or 020 whatever, it wouldn't have an effect on my stroke status. However, sometimes you may take it, in a lightweight like that, or in a very lightweight like that, but you don't know what is going to happen. You are not so much of a mathematics genius. So the best way to determine whether um, a feature is significant to predicting to predicting, let's say an independent variable is significant to predicting a dependent variable, is to use statistical methods. You cannot just sit down and use your head and be like, no, this will affect, this will not. That will be a random guess, and it is going to be an uneducated guess. So we have to, at least if we are guessing, let it be a well-educated guess, right? So sorry guys, my throat is very dry. My head has started itching. I had to take water. So we're going to use statistical methods to determine which feature is actually significant or not. Now, we have most ways of doing that, and one of the ways of doing this is what we call the F classic, as you can see here, or the select k best. So we have a lot of ways. One way, I repeat, is the F classif, and then the select key best. Now, the F classif is simply for um, Fisher. F, who knows F test? In those who have higher statistical, those from the math background, you've heard of F test, T test, Z test, and all this. So F test is Fisher test. It was a man, a great mathematician, statistician called Fisher. He has a test more like ANOVA, analysis of variance, where we check the means to see whether something is significant to the other. There's a lot of mathematics in there, but if you want to know much, I'm not going to go so much detailed into that before I start, you know, confusing most of you guys here. But if you want to know much about that, then probably you can search on the internet or you go to YouTube, type F test, and it will F test. Test as in TEST. F as in the letter F. F test, and you know a lot about that. So we use F test to determine which independent variable will be best predictor for predicting the dependent variable. Yeah. So now we have to import um, the F test, and then the F test in for classification in Python. In scikit-learn is called F classif. So F classif, maybe F for classif is obviously the short form of classification. So we are importing the F classif, and then the select key best. I'll talk about the select key best from feature selection, module. And it is obvious because it is helping us to select some features, the significant ones. And now back to the select k-best. The select k-best is simply to tell Python that when you run f-test, maybe I want you to select the top 5 significant independent variables, or select top 10. So k is actually telling, or the k is standing for the number top what? Is it top 10, top 2, top 1, top 20, top n, something like that. So top k best, something like that. So it's very simple. Now the next thing is we've already imported make pipeline top there, where we actually importing pipeline itself. It's the same thing. Make pipeline and pipeline are the same thing. Here we're going to make it in a format. We're going to automate it. So in the pipeline, we're going to have a stack of activities going on in the pipeline. So more like if this is the pipeline, the data will enter here. Something should happen at this stage, happen here, and then output it, something like that. And then another thing is, before um, we used to impute the values. Imputing meaning we used to replace the missing values ourselves. More like we have to do the mean and then the median, and then we kind of see, okay, this one is this and blah blah blah. So here we're not going to do that. Mind you, we're going to automate it. So we importing what we call simple imputer. So simple imputer is a way to impute, automatically. So we can tell Python, hey, I don't want to write the codes myself to say, okay, use impute to the this. So I want you to impute it, and then it takes an argument called strategy. The strategy is actually what do you want to impute it with? It can be the mean, the median, it can be the mode, or something like that, a particular value you want, or something like that. So that is one thing you should know. And then here we're going to create a pipeline, and I'm saying that I'm just calling it pipeline. So I'm saying that I'm sorry, I'm actually saving it in a or keeping it in a variable called pipeline. So I've imported pipeline up here. So let me maybe create a listing up here, and then so I'm saying that from pipeline, um, in pipeline, I'm going to have, so we pass it in the form of a list. Since we have more than two things, one thing going in there, let me split it open. And the first thing, which this is how we do it. So you put everything in a listing, in a list, and then in the list we have tuples in there. Every one thing is going to be the tuple. So the first thing I'm going to say is, okay, in this pipeline, when the data enters, now, the first thing is there may be some missing values in there. For example, it's, the BMI. You can see there are some missing values in the BMI. What I'm going to say is I want to impute them first. those missing values, I want to impute them. I want to replace them. Now, the way to do the pipeline is first give a name. So give a name to that step, that particular step. So the simple imputer, the stage where I impute the values, I want to call it imputer. So imputer. And then the next thing is to call the simple imputer this thing. And then it's a function, obviously. So you pass in the strategy keyword, and then the strategy, I'm saying that okay, replace it with a mean. So when you go to the BMI, when a value is missing, replace that value with a mean BMI. Simple. Or whichever feature which has a missing value, when you, if it is numeric, then replace it with a mean. But we know that it is only BMI which is actually going to, which is actually having missing values. That is why we specified it to be the mean. Yeah. Now we've done that, so we do our comma, and then we bring the next thing. So the next thing is now we want to do the F test first. So I'm calling it F test, and then it is going to be the select key best. So the select key best, and then we pass in one argument called the score function. So the score func, which is a short form for the score function. So if we want to select maybe top maybe 10 or top 20 or top whatever, but on which basis? I want to say that um, I want you to select on the basis of F test, which is called F classic, which is called F classic, which is how we call it in Python for um, logistic regression. So simply we've built our pipeline. So if I run this, hopefully I don't get any error, and you can see. So it's more like a pipeline. So this is a pipeline. When I open it up, when I click on this drop down, you can see that. So this is a pipeline. First, we have a simple imputer, and then we have the select keylist. So when we pass the data through it, it will first, at this stage, it would impute the missing values. Then it will go to the second stage to go and then do the F test to see to calculate the F test to tell us which independent variables are significant in predicting or will be good to predict. Significant, I mean, will be good predictors or will be good in predicting the dependent variable, which is true. Then it outputs it for us, something like that. We can add more than two. It can be three, four, five processes, but this one we want to keep it two. We just want only two things. So now, after building the pipeline, you have to train it. Training it more like you have to now, not like train it. Now you have the pipeline. You have to now let's pass the data through it to see whether it works. And to pass the data through it, we just do the dot fit. So we want to pass the data through the pipeline we've built so that it calculates the F test for us to see which one is significant. So just like we will do the pipeline dot fit, and we fit it with the independent and the dependent variable. So we will pick each of the independent variables. So for example, if you pick gender, it will compare it with stroke to see is gender significant, is gender actually a good predictor for stroke. If yes, fine, it will calculate its metrics and then keep it and do it for all the independent variables. So that's what we're going to um, do. So let's not forget to, so let's call this P, just P for short, P. So to train, we just do P dot fit. We want to fit it with the independent dependent variable, and it has trained very well. So simple. So that is what, and then I wrote this thing here. So if you don't choose, so you can choose not to state the strategy of the simple imputer. You can choose not to provide a strategy, and then the default value in there is mean. So if it is mean, we can choose to not bring this. If you want to impute by the mean, you can just leave it like this, since the default value is mean. Or if you are like me who is curious, I just brought it for you to see. So if you want to impute it with the median to you do that. Now to input to determine whether you impute it with the mean or the median, it would actually be determined by your um, so it will be determined by the distribution of the variable. I always say. So for example, if we do df BMI dot hist to look at the distribution of BMI, if it is, we can see that it is kind of skewed. So if you do, for example, let's do the mean. So the mean BMI, um, you suppress the output. So the mean BMI is 28.89. Now let's look at the median. So the median is also 28.81. So they are not really far from each other. So we can use any of them. But if you have a data where the median is kind of far away from the mean, then it is always, and it is obvious that the the data has some outliers, and it is best to use the median. But since they are not really far from each other, let's use the mean. But you can choose to use a median if you want. Now we've run our check to see which features are significant, which one of them are not. Now let's come to how to get. Now let's see which we don't know yet which ones are actually significant, which ones are not. So we're going to for F test we have the F test score, and then we have the p values. So the p value is more like, you know we have two values. You have the F test, that is the F test score. The score we ran F test on it. What was the score of what was its score? And then we have the p value. So the p value is um, more like a tag attached to it. So I don't know whether any of you have heard of who hasn't heard of p value before in statistics. Who has never taken any statistics course before in this class? Just raise your hand or you can unmute yourself. You've never taken any statistics. You've never heard of p value. So Rashad, you've never heard of p-value, right?
No, I've not. This is my first time.
Okay. But have you heard of T F test before?
All those terminologies are actually new to
Okay,
me now.
that's fine. So let me do my best to explain this to you. Um,
All right.
the rest are cool. I know all of them are. Abubakar is from engineering background, so he will surely have. Anamwa, Samra, Fauzan are also way. Nanamwa and Sandra are from actuarial science, heavy maths background. Fauzan from business. I know he does. I know they have this stat course, which is always worrying them. Yeah, I know about that. My friend was in business school. So the p value is more like um, see it as maybe a score. P for maybe let's call it power. So how the power of it. So um, we can say that we have something in statistics we call confidence level. So confidence as I am confident. So your level of confidence is more like to tell us how confident you are. So if, for example, if I say I am, maybe I'm going to do something and I say I am 95% confident that this will work. So what it means is that my belief in this is actually 95%. And if I give you something, maybe a machine, and says that, let's say we're going to, let me bring it to our level. We're going to write exam, and then someone drops a question, maybe WASI or BEC, let's say WASI. And then they drop an apple, and they say that this apple is um, the assurance, or let's say the rate at which it will drop is actually 95%, meaning that it is 95% kind of like assured that a beba, a betu. something like that, upon Ebetu. And it is in the other way around, there is 5% chance that it will not drop. The Apple will not drop. You get it? But the higher the confidence interval, I mean, the better the thing is. If you have something which has 95% chance of happening and then 5% chance of not happening, then you'll be confident enough by using the thing. If you are sick and they tell you this drug has 90% chance of healing you and just 10% chance of not healing you, you would be okay. But if I tell you this thing has 10% chance of healing you, 95% chance of, or 90% chance of not healing you, you'll be like, ah, Charlie, what's up? Then it is better I don't take it because there is higher probability it will not work. So in statistics too, whenever you're running any test or anything, you check for confidence interval or confidence level, sorry. So confidence level tells more like the scenario I was giving. What is the level of confidence that this thing is going to happen? So it can be the popular ones are 90%, 95%. Yeah, I think those 95% is always a problem. So you hear confidence interval of or confidence level of 95 or 0.95. So if you have a 0.95 or 0.95 confidence, then it means that you have in the other way around or the vice versa, you have 0.5 or 5% chance that the thing will not happen. So the p-value is actually a value which is telling us it's more like a score, or a value which will determine whether the thing is in the significance or the acceptance region, is within the confidence region or not. So the p-value is a very small value. So if we have, let's say, 95%, 95%, let's say we take our confidence level to 95%. So we're building a model. We're saying that we want our model to be predictions to be 95% sure, meaning that we want the model's percent to be 95%. The model's score or performance or prediction should be 95% true. So if it tells you you have stroke, it means that it is 95% true that you have stroke. So it has a higher accuracy or more like precision um, score, meaning that Charlie, if I have 95% accuracy, it means that 95% of the time, what I'll do will be right. Only 5%. So if I tell you you will die, then you have to start worrying, something like that. So in the same way, the p-value. So if you have 95% confidence level, the other way around, or there is 5% chance that that thing will not happen, and that 5% chance is always called alpha or the rejection region. So alpha, let's say alpha, it is called alpha. Alpha as in the letter alpha, the Greek letter alpha. So the alpha is the vice versa of the confidence level. So now the p-value is a value, and always if you have a confidence interval, then any p-value which is, you know, I hope I don't get it wrong, which is greater than the if the p-value is greater than the alpha, then it means that that particular feature or that particular independent variable is not significant. But if it is less than the alpha, then it means that it is significant. That is one thing. So I don't know, Rashad. I don't know whether I've been able to explain to you. Sure, I'm glad. So now we taking that p-value and then the f-test score from the pipeline we created up here. Now, and then we convert it into um, a data frame as usual. So we have the features here now, and we sort it in ascending order. So you can see them here. Age is the most significant, having a p-value of almost zero. So it's like 0.0 up to somewhere 7, which is almost zero, right? And then it has F test score of 326.9. So let me explain. The smaller the p-value, the better, the more significant it is. And then the bigger the F test score, the better it is too. So the F test has a different or negative direction with the p-value. For the p-value, it has to be very small. So the smaller the p-value, the better or the more significant that particular variable is. And then the bigger the f for the f test score, the bigger the f test score, the better. So you can see that when you look at age has the highest or the largest f test score, and it also has the smallest p-value. So the smaller the p-value, the more significant it is. So if we take a confidence interval of or a confidence level of 95, meaning that we want our model to be 95%, its prediction to be 95%, more like have 95% confidence in its prediction, then alpha would then be 95 minus 100 minus 95, which is 5%, which is 0.05. So any feature here which has a p-value which is greater than or equal to, or let's say greater than or equal to um, the p-value, oh, sorry, the alpha, which is 0.05, then we have to reject it. I repeat, if we pick a confidence interval of 95%, alpha will be 0.05, which is, uh, in other words, which is 5%. So any feature here which has a p-value greater than 0.05 will be rejected, meaning that it is not significant. So we don't have to include it in the model building. We don't have to include that particular feature in model building. Thank you. So I wrote something here for human health analysis. Human health analysis is very, very important. We normally take a very high significance level. It can be zero, it can be 99% confidence level, it can be even 99.9% sometimes. So if you take 99%, for example, then the alpha level will be just 1%, and then that is equivalent to 0.01, or even less. Sometimes you take 99.5, 99.9. But this is just a demonstration, so we taking 0.05, meaning a confidence level of 0.95 or 95%. So, like you can see here that age is the most significant. And when we take that, all these guys here, the top 10 are actually significant, except residence type, which has zero point 0.2, more like zero point 0.0, is it 0.02? Yeah, more like 0.2, yeah, zero point 0.2, which is not which is greater than 0.5, 0.05. So we reject this, we don't include it, and then this one too. We don't include the last two, that is gender and then the residence type. They are not significant. So we've seen how we can use F-test to kind of know how which features are significant, which features are not. And then after knowing that, now let's drop those ones. So we drop gender, we drop um, residential this thing because they are not residential status because they are not significant. And then we we proceed to split our data into training and testing as usual 80-20 rule, meaning 20% for training, 20% for testing, like we did before. Or maybe let's make it 90-10. Yeah. So when we do that, I didn't run this guy. So when we do that, we have it here, and then we first build a logistic regression. Let's build a linear logistic regression first, like we did before. So I'm importing logistic regression from sklearn.linear model, and I'm importing something called cross value cross val score, or um, we call it cross validation. So cross validation is more like it is a way to improve models performance. So it is more like an iteration. I don't want you to just do one thing to just build a model. I want you I want you to iterate through the model. More like a number of times I will specify. You get it? And then if it is iterate through maybe 5 times, for example, or 10 times, and give me the score so that I pick the one which performs better. So that is a way to also improve models testing. So here we're going to build a pipeline. So the model we're going to build a pipeline. I'm calling it the linear regression model um, LR, or for logistic. Sorry, I said linear regression, logistic regression. So it is. I'm calling it model LR because we're not going to build only one model. So to differentiate, I'm not going to call it just model. Yeah. So model is what is going to, or let me demonstrate it up here. So we code going to, let me call it M here. We're going to create another pipeline, which is um, going to house a pipeline for the model. And the first thing is going to be an imputer. We want to impute the missing values. That's for what do you call it? BMI, and it's going to be a simple imputer. And you see here, I'm not going to specify a strategy because I said up there that we want it to be to impute by mean, and that is the default. So even if you specify it or you don't, it's going to do that. But if you want to impute, for example, by the median, then you have to specify. So let's say strategy is equal to median. Then you have to spell median correctly. Now after imputing, we want to now build the model. And we're going to call the model logistic. I hope I spelled logistic regression. And then that is going to be a logistic regression. And in there, before we didn't, when we built the first logistic regression, we just did logistic regression. We didn't specify any parameters. Here, we're going to specify some parameters. And let me just show you some of the parameters of logistic regression. So if I do logistic regression, you can see that it has a lot of um, hyperparameters or parameters in here you can specify. And these ones will determine the behavior of it. So when you tune them well or when you set them well, it will give you higher performance. If they are not set well, it's so how you set it actually has an effect on the performance. Now we have a lot of them in here. You can see they have default values. That is why even if you don't specify anything, it still works because it takes the default values in there. Now I'm going to specify a few of them, which I'm going to specify the solver. You can see here the solver is actually um, how it solves, and then it has three things. We have the lib linear, we have the LBFSGS, and the other one I think I forgot. I think yeah, which is a combination of the two. And then we have penalty. Penalty is more like how so if the model predicts wrong, it's a way to kind of minimize the error. So if the model predicts wrong, we want to penalize the model by kind of like telling it that go over it again until you get it. You get it. So when the model predicts, we want to kind of add something to it or subtract something to it so that it kind of gets close to the actual. And C is also so the penalty has three ways we can. We have the L1, which is the lasso. Sorry, the ridge we call it rate regression, and then we have the L2 penalty, which is the last one. You can see the default is L2, but now we are going to use L1. And if you want to know why, you can read more online. You can, there is a lot of resource. Because of time, I cannot teach you everything. And then we have C. C is like more like um, the default value here is 1.0. I'm setting it to 20, and the thing is, C is more like it's like telling the penalty more like how many iterations you're going to do and all those things. It's more like the opposite of the penalty and helps in the model's behavior. So quickly, let's go and do that. So I'm going to say that logistic, sorry, solver, the solver is going to be a linear one, linear, and then the penalty, I'm going to pick L1, which is ridge regression, if I'm not getting it wrong. And then the C, we're going to, so you can on your own change the C to different values and you see the effect. Yeah. So now I've built a pipeline. You can see that we have a simple imputer. So when the data is actually fed in here, it will first run through the simple imputer and it will replace or impute the missing values before it goes to the model. Yeah. And you can see that the model has some hyperparameters. So now after building the uh, model, after building the pipeline, let's now train the pipeline, fit the data. So let me call this pipeline maybe um, Now let's train. So we do as usual, but fit train it, or we train the thing on the training data, and then when we run, it is just finished training. Very, very quick. Now we're going to, if you now let me just quickly show you. So if I want to let me do dot score extreme training. So we have a training um, accuracy. We have an accuracy of 0.95 or 95%, like 95.22%, which is quite okay. But I'm going to show you something very soon for you to know why this is not okay. This is not a good performance for us. Now, um, before I come to that, I have, this is just one iteration. I want to say that, hey, don't just do one kind of like iteration. I want you to go kind of more like go over it again for me to see whether it can improve. So that is what the cross validation score is going to do. So when you come here after training, I'm going to say that I want to do a cross validation, and the cross validation is more like to repeat, you know, and then whenever you do um, grab the training score or the accuracy, put it somewhere for me, and then let me compare to see the highest accuracy, and then probably use that model, which is going to be the best. So now this is how we do it. Very simple, just like here. So we call the function which is cross validation score, and then we provide the model. So the model is actually going to be um, the model we built. We called it M, right? Yeah. So we stored it in a variable called M, and then we provide the data in which we want to do the validation on the cross validation. So we want to do it on the training data, and then the next thing is CV. So how many cross validations, how many iterations do you want to go? So let's say 5. If we do that, then when we run, you can see beautifully here that it did 5 iterations. And in the first training, so it will train the model like 5 times and see. So the first one, you can see that the model, the performance was, or the accuracy was 95.1, and then it trained again, it got to 95.21, train again 95.21, train again 95.1, 95.21 again. So you can see that from the first iteration, the the when it trained it in the second time, the accuracy kind of increased. But after the third iteration, it didn't increase again. It started to drop. So it is telling you that maybe if let's set it to 10 and see to do 10 training, and you can see that the first training, the first evaluation, we got 95.21, we got another 95.21, 7, the same thing, we got the same thing, we got the same thing here, almost the same thing throughout. But when you go here, you can see that it's kind of going down. You can see it. So it is telling you that the best it can do is probably 95.21, and we will know why it is so. So this is a way to kind of the best way. It's a technique to improve your model's performance because you can see the highest accuracy you can achieve, and then you use that metric, and that is something very good I wanted to show you guys. And then we print the median score or the mean score, the average score, average training score, which is like 95. That is the average or the mean of all these guys here, which is like 95.42 or 43. Yeah. So now it is a good thing. But the thing is, when you look at the class balance, if you look at, for example, if you do df stroke and you do the value count, although our model's performance is nice, and let's say when we do normalize um, equal to true, we can see that 95% of these guys of the data sets did not have, or the patients did not have stroke, and only 5% had it. So what the model is doing is that it is just, you see the model's accuracy to is around 95%. So what the model is doing that is that you can quickly see that the model is just learning how to predict those who did not, you know, those who did not have stroke. So it is doing well on the like no class, but it is not going to do well on the yes class. And it is a common problem, a very common problem in classification. Whenever you have a data, you can see that this one, the classes are not balanced. The yes, those who had the patients who had stroke and those who did not have, their proportions are not kind of like balanced. You can see the numbers are not balanced. This one, 95% of the people did not have stroke, only 5% had. So the model is just like a human being. It will learn to be more like biased. So it would be like, okay, it's just like a smart kid. You will see machine learning as a smart kid. You'll be like, ah, I be the thing cry. It's like, I be the thing cry. 95% of them are no, no, no. So let me just focus on the no, no, no. So when you bring it, you be like, no, no, no. And then you may think it is genius. It's like doing, there's this game we used to do when we were young. Um, Cocoa and Tum Cocoa and Tum. We use Spa. Who has ever played that game before? Raise your hand. No, Spa, the cards. I mean, cards. Whether it is red or black. You kind of ask Cocoa and Tum. Okay, Sandra. Yeah, that's true. Sandra is a G, right? So it'd be like cocoa and tuntum. Maybe I'll say tuntum, black. I mean black or white. I think all of us understand tree. So cocoa and tuntum, I'll be like, oh, cocoa. So if it is cocoa, you give it to me. But let's say I know I have studied the cards and know that there are more red cards in there than black. All I have to do is, I don't even need to think about black. All I have to do is, whenever you ask me, I say cocoa, 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 because I know in the end, even if I don't get even just a single black one, and I get all the red correct, then I'm going to win because the red cards are, quite, they are more than the black cards. So that is the situation here. The model is saying that, okay, I be 95% of the guys they don't have stroke. So let me just focus on them. Whichever patient you present to me, I'll say no stroke, no stroke, no stroke. And you can see that ideally in the data sets, most of them too did not have stroke. So it will have a higher accuracy, but don't just be fooled by that. Always look at the class balance. So in this case, when we have this, when we have a situation whereby the class balance is very, very, very huge, where we call it imbalanced class. So when we have a class, or let's say a data set where the classifiers or the categories are heavily different, we call it imbalanced. You have to balance it to give it 50-50. So it's more like, yeah, if you want to see you are a genius, Sandra, you remember, if you want to see whether you are a genius or not, then maybe when you have 100 cards, pick 50 of them to be white, red, 50 of them to be black. Now let's do the cocoa or tuntun game. So if you say cocoa, you get 50, I'll get 50, no one wins, right? But the genius will be the one who will be able to perform or be able to predict both black cards very well and then red cards too very well. So you have to get more from red, more from black. And then in that way, you can get the majority. So always the model is the model has to perform well on both classes, not just the no classes or yes classes. So that is one thing you should put in your head. Don't be fooled by, it is something very simple in beginners in machine learning. They'll be like, Charlie, see, I built this model and it has 99% accuracy. Now go back to your class, the data set and check the class. Maybe it might be from the distribution of the class balance. You get it? So we've seen here that 95%, 95.12% of the data, the patients had no stroke. So it is not so surprised our model is performing this way, right? So the model is not performing well. On it is performing well on only those who did not have stroke. But now let's analyze this. We have a model. Our aim is to predict those who will have stroke so that we, in the early stage, and then we kinda help them, we treat them, we recommend them to doctors so that it doesn't grow into this thing. So our focus is more on patients who will have stroke than those who will not have. So we want the model to perform better on patients to better classify patients who will have stroke correctly so that we can help them than those who will not have. So always put that one in mind. Nowhere, we will talk more about that later, but know what you wanted and how the model. So let's see how we can address this. Maybe, yeah. So let's make some predictions here. You can see the training accuracy. Once again, the training accuracy is 95.42, which is not so much over 95.12. So just 0.0, so like 0.3% more, meaning that it didn't predict most of the this thing, the yes or the stroke patients or the patients who have strokes, correct. So let's just run this guys, and you can even see we have 95.19, which is something very just 0.00 0 maybe 2 or 7 rather, yeah, something like that. Now let's perform another 10 cross validation and see. You can see that nothing really changes that much, and um, what am I doing? I change the thing up there. I think I didn't run this guy. Okay, so we've seen things are working quite well. Let's run this guy again. So we've seen that our model has higher accuracy, but it's not performing well. Let's make some predictions here, and then we find this thing. We can see that I have 94.52 testing accuracy, which is not good. Um, so the model does not even generalize well. Now let me scroll down here and pick this code here. Maybe we can let's create a confusion matrix and then we interpret it. Maybe it will help, right? So that is before we even go. I want us to look more into how or why I'm saying that the model's performance is not good. So the model is model RL, and we want to kind of look at how the model you know does what the this thing. You can see, or let me use the training data sets rather, so that we see what I mean. Model dot. So let me copy these guys and then bring it down here and change it to the training. I want to explain the um, confusion metrics, and also I want to I want you to know why the model isn't. This is two. So we have a training accuracy of 95.4. Okay. So now let's do this and see. Now this is the confusion matrix. This is how it is. Bear with me. Let me explain it to you. It is very very simple. So you see we have four sections. Now we have on the vertical, on the horizontal axis, we have predicted labels. So meaning, and we have 0, 1. And then on the vertical axis, we have true labels. We also have zero one, just like that. And you can see a color scale here. Now this is what it means. You know, on the when you pick the um, when you come to the horizontal axis, that is the model's prediction for the classes: zero for no stroke, one for yes stroke, obviously. And this on the vertical axis, that is the true labels. That is actually what was actually in the training. What is the actual this thing? We predicting, training the model to predict, and we have the data already. So what was the actual class of the person? Was the person one or zero? That is what the true label means. Now the intersection of it. So when we come to this box, so we can see zero here, so and one here. So this box is telling us the you see the number is zero. So this box tells us the number of predicted, um, the number of patients the model predicted to be zero, or to be in the zero class or to have no stroke, but we're actually, but we're in the true level or in the reality they had stroke. So zero, it predicted zero, but it is actually one, which is it predicted no, it was actually one. When you come to up here, so you can see this intersection of zero and zero. So here it is talking about the number of patients or the patients the model predicted no, or maybe not to have stroke, or in other words not to have stroke, and actually didn't have stroke. The same way when you come to this box, that is the intersection of 1 1, telling us that the model, that is the predictions the model made, or the yes, um, the patients or the number of patients, or let's say positive, one for positive, zero for negative. So the positive class, more like how many patients did the model predict to actually have stroke, and then how many of them, were actually having stroke. So one, the true label was one, and the model also predicted one. When you come here, the predictions the model predicted to be, one, but it was actually zero. So this box here, so when you look at it, the diagonals, this diagonal is actually, or let me take it, this yellow one is telling us, this diagonal is telling us actually the true labels. So the ones which were actually, the model did the correct predictions for the model. So the yellow one here and then the one here. So the diagonal like this, these guys are telling us the true, the models, the ones the model got correct. So the yellow one for the negative ones or the no ones that it got correct, and then this one, the down one, is telling us about the one it predicted yes or one and it was actually right. Another way, the diagonal like this is also telling us the models, wrong listing prediction. So you can see the down here is telling us the number of the negative class or the zeros the model predicted, which were actually one or which were wrong, and then the number of yes it predicted, which were actually no. So when you come here, you can see that the model predicted 4,598 no's, which it got actually correct. It never got, you can see that the model never did any mistake. It predicted very, very well. So we gave it 45,000, 4,599 data sets, but it predicted 4,598 of them to be no, yes, they don't have stroke, and indeed they did not have stroke, which is awesome, right? So it is a good thing. And it predicted one patient to have stroke, and indeed the person has stroke. So you can see that it never did wrong with the negative class nor the positive class, right? It is a good thing. But one thing you have to know is that we have 4,599 data sets where only one patient actually had, stroke. So it is easy thing. But in reality, we wouldn't know whether the person has stroke or not. So we don't want to build a model which is quick to judge. It should have fair like 50-50 knowledge. So it is not always good you train models on very imbalanced data sets. So this is a confusion matrix, and it is an advanced way to look at the models, an advanced way to calm down, let me finish explaining. It's an advanced way to look at the models, to evaluate the model's prediction. Rebecca, ask your question. Yes, Siddiq, your hand was up. Your hand was up. Please ask a question. If there is no question to Charlie, let me. Okay, my phone fell. It's a mistake. Sure, no problem. So, guys, that is how the confusion matrix is. At least I think it's easy to interpret. Very, very easy. You know, so the predicted labels, true labels, so their intersection will tell you. So, zero on the predicted label, one here, the intersection of 0, 1 is telling you that the ones you predicted to be 0, which were actually, 1, and then the yellow one up there, that is yellow one up there is intersection of 0, 0. So the one you predicted to be 0, which were actually 0. And then when you come here, 1, 1, telling us that it is the one you predicted to be yes, which were actually yes, or which are actually no. The top one, the one you predicted to be 1, whilst it was actually 0, something like that. I hope it is quite easy. So now, Larry sent me one strange message. So now we've seen how to build a linear regression model, automate and all those logistic regression model. Sorry. Now let's come straight to building the random forest classifier. Now here we're not going to do um, all those encoding ourselves and all those things. We're going to look at how to automate things to make things easy for ourselves. So, whew, coming, I'm tired. Let me take maybe some few seconds rest. So, we're going to look at this is the second chapter of it. We're going to look at the random forest classifier. Now, random forest, random forest classifier is actually a more advanced model which is first non-linear. Non-linear in the sense that logistic regression is a linear model, and maybe in our next meeting, you'll know why it's a linear model. And if you are very curious, you can just search on the internet. Now, you don't wait for somebody to tell you information. Whenever you hear something new, blah, 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 why is logistic regression a linear model? You'll know why. Now, sometimes, the model or the data will not suit for linear models. Linear models kind of look at the linear relationship between things. Sometimes the relationship between two things or two or more things will not be linear. It may be very complex, like in society. Sometimes your family, it will not just be this is my brother, this is my sister. It might be that this is my father's uncle, brother, sister, nephew, son, which is a weird, very complex, relationship. So linear models like logistic regression perform very well on linear data which has linear relationships. But the when the model or the data is having complex or non-linear relationships, then it's linear models like logistic regression do not perform well. Now, how do you know whether the data isn't linear, doesn't have linear relationship or not? When we did the correlation, you could see that they didn't really have strong correlation. So when you have a data frame, you want to build a classifier, but you can see that the independent variables do not have strong correlation with the dependent variable. In that way, it is better use a non-linear model like random forest or decision tree classifier or maybe SGBoost or cat boost or any of them than to use logistic regression. But when you see that maybe the correlation between the independent variables and dependent variable is strong or quite strong, then linear models like um, logistic regression will really work. Another important of using nonlinear models like um, random forest classifier is that um, when your data set, the independent variables kind of are not uniformly skewed, they have outliers and all those ones, then the linear model tends to, since it is linear, it tends to kind of go wayward. But when you use a non-linear model, it kind of knows how to handle that. So that is one of the advantages of you know using non-linear models. Not to say that linear models are not you know they are not important. They are really important. In fact, we use them to build very robust models. Myself, I have worked for SIC Ghana, built a very robust um, um, model for them using logistic regression for customer what do you call it, claim risk assessment. And it was, in fact, it did better even than the non-linear models because the data had linear relationship. Period. Now, enough of the talk. Let me introduce you to random forest classifier. First, it is also a supervised classification algorithm or machine learning algorithm, but it is non-linear. See it to be like this is how it works. It is like this factor tree I was telling you. This is not the first time I'm telling you about logistic regression. It is like this thing in high school. We have this even in basic school factor tree. So you have 32. What are the factors of 32? You do 2 times 16. So you draw, you write 32. Then you bring two like two lines down here. So 2 times 16 will give you 32. 2 cannot be factored down, so you leave it. Now when it comes to 16, it can be refactored into 2 times 8. 8 can be refactored into 2 times 4. 4 can be 2 times 2. Something like that. So um, that that is how random forest kind of work. It works on the same thing, like it's almost same principle. So when it picks the data, it will split it into maybe two or three, based on what you say it should do, based on what the nature of the data set. Then it will be kind of like dissecting down into it to learn the relationships. More like when you pour water into maybe on a floor, an even floor, it will find a way through things, due to relationships and all those stuff. That is how it works. So you can read more on logistic, random forest classifier. The one thing I want you to know also is that it is called an ensemble model. Ensemble, Ensemble, from the word assemble. So when we say you're assembling something, like more like bringing a lot of things together. So we're assembling a car, we bring the tire, bonnet, and all those body seats, put them together. So linear, this random forest classifier is actually um, an ensemble model. What it means is that it is a collection of it is not just one model like logistic regression. It's a collection of models in there. So like a lot of models come together and then they form that random forest classifier. That is why it is also very, very important. So it's not just one model working. There may be 10, 20, 100,000 models or the number of models you specify. So you specify the number of models you want. So number of models coming together to work. So you see, there is more like division of labor, and then when a lot of people work on something, they say two is better than one. So that thing also holds here. Yeah. So sorry if I'm a bit slowing down. I'm not really fine. My head has started aching, and I'm feeling weak now. But we have to finish it. Don't worry, I'll be fine. So um, so cope with me if I am kind of relaxing. So that is how it is. It uses a technique called bagging technique. Bag as in your bag. Bagging. So bagging technique is when we have we have this lot of models. But what it does is all of us, the bagging techniques, all the independent, let's say we have 100 models in there. And those models are what we call decision trees. So they are decision trees. Decision tree is also a model on its own. Maybe our next meeting we'll look at that. But random forest is a collection of decision trees. That is why we call it's a forest. It's a collection of trees. So a collection of trees is actually a forest. Very funny name, right? So decision trees, let's say 100 of them. So each of the decision tree models will make a prediction. For example, if we pass in data, each of the 100 decision tree models or unit models or sub models will classify the patient whether it is one or no, yes, or whether the person has stroke or not. So when all of them finish, then we kind of vote. They vote to see which one is the majority. What is the majority? So if one is the majority, then they pick one and output it to you. But if zero is the majority, it picks zero and give it to you. Another way, it can also, if it's a continuous value, then it will find the average and then give you the average, something like that. So it is always, more like more sophisticated as compared to um, logistic regression and code. So enough of the talk. Let's go into it. So now we're going to, like I said, we're not going to use this. We're not going to hard code, hard manually encode them. Sorry. Oh, nope. Sorry. No, it's not easy. So we're not going to um, manually encode the marriage status and all those guys. So we're going to drop all those guys in there. So we're going to drop the ID. So we're going to, what I'm going to do is just split them into training and then um, the independent variables. Again, I want to show you how we can automatically do the encoding, not manually doing it. So we do the X or independent variables are actually going to be, we're going to drop the ID. You know why stroke is dependent, so we're not going to add it. And then all the encoded ones we did, we're going to drop them. You don't need them so that we get the original this thing. And then the Y, the dependent variable is going to be stroke. And when we do, you can see them. Now, if I do, if you want to see, so if I do X or head for this thing, you can see that we have age, which is male, female. We've not encoded any of them, like the normal thing we had. So now let's split it into training and testing. So let's use the um, 90% for training, 10% for testing, and voila, there we go. Now, if you are curious, if you look at Xtreme, you can see that it still has the unencoded stuff in there. So now this is my frame, or this is how I built my listing. I first my machine learning. This is my machine learning workflow. So I first use the baseline. The baseline is more like what is the baseline, what you don't want to go beyond, or let's say below. you know. And then you have to now iterate through, and then you have iteration is more like you build a model and then you kind of like repeat it until then when you build, you evaluate. If you like the metric, if you like the performance, you keep it. If you don't like, you come back, you iterate, and then you evaluate again until you get what you want. And then you now when you finish, you communicate the results more like you now deploy the model. Because me, I work for my boss in this thing, I work in the research lab. I communicate to them, hey, this is how it is. And so now let's look at the baseline accuracy. Now we know that when we look at the class balance, when we do DF, when we look at this class balance for stroke, when we do a value count, we can see that um, hmm, yeah, if we do a value count, you can see that majority of them do not have stroke. And if I do normalize it, it's equal to true. You can see that almost 95%. So let me multiply it by 100 so that we see the percentage drop. So we can see almost 95.13% um, are actually they're actually not having this thing. So the baseline is you want to build a model which will have an accuracy above this one in here. And if I want to take only this guy, if I run, you see I get all of them. If I want to take, I can take the maximum. So the maximum, if I do dot max, I run, I get only the maximum. The same way if I do dot main, I get the smallest. But we want the maximum, and that is the baseline. So the baseline, we want our model to at least perform, you know, it shouldn't be below the performance, the average shouldn't be below 95.13. And that is what we say here. So we're setting the benchmark for ourselves. And we want to build a model which performs better than this. Now, I'm going to use the pipeline again. And the pipeline, in the pipeline, I'm calling it CLF for classification simple. So in the pipeline, let me do it up here. So I'm going to build a pipeline. Instead of using the pipeline, I'm using the still make pipeline and pipeline are the same. Now, um, let me come here. So I'm going. So in the pipeline, I first want to impute um, missing values. So when you input data, if there are missing values, impute them. I'm not going to specify the strategy because I want to use the default one. That is the mean. I want to impute it by the mean, and then after imputing, I want to encode it. So I want Python to encode them using ordinal encoder. So ordinal encoder is more like when you read the documentation, sorry, on random forest classifier, the people who built the model say it works well with ordinal encoder. So encode it ordinally. Now, what ordinal encoder does is that it encodes just like the normal one we do. The normal one is this, two is this, but it tells Python that one has, it's like it is in order. It has order, whether ascending or descending. We leave that one to the model. It would figure it out on its own. So it will study the data it can do. That is why it is machine learning. So learn on your own. Now, after encoding them to the way the computer likes or the computer understands, we want to now build a model, um, not a logistic regression, but a random forest classifier. And since it is the names even suggest random forest, we want to keep whatever it does. We want to kind of stabilize it. So I will set random state is equal to a number with my favorite number, which is 42. Now, if I do this, you can see that now the pipeline has three things happening in there. First, it will first impute missing values, encode the data, and then now you know, pass it on to the model. So that is what we're doing in there. And now, not just that, after building the model or after building the pipeline, we also want to use grid search. That is more like we want to kind of iterate through to get the best hyperparameters. Now, hyperparameters are those things you see the when you build model, like this thing. The things we pass in here, the parameters we pass in here, random state, maximum, test size, those things. The things, the functions that go or the things that go into the brackets. Now, the hyperparameters are the ones we call them hyperparameters because we can set them before we even train the model. So we can actually specify what we want. So like you see the logistic regression, I set the solver and then the C and then the penalty. So those are the hyperparameters. So they determine the behavior of the model. So we can set them before. That is why we call them hyperparameters. So we can set the one we want. So here I'm going to first do an advanced hyperparameter search. So what I'm going to do is I'm going to say that, hey, I want to create like more like a list, a dictionary, which will has a lot of things in there. I want you to iterate through, combine this and this, go through, combine them, and then when you combine them, now give us, you know, combine them in the way you want, and then pick the best out of that, and that's boom, that's all. So I this is how we do it. We pass it in, we do research, and we pass the parameters or the set of parameters in the form of a dictionary. So the head or the key is going to be, so first I'm going to go in order of my listing. So either I have a simple imputer. So I want to say that simple imputer, and then this is So simple imputer, then underscore underscore. So what simple imputer this thing parameter? I want to set the strategy to. I'm saying that okay, I want it to be most, and then you pass the keys in the form of a list since it is more than one. So I'm saying that I want it to be the most frequent one. So meaning that if you pick a particular listing, like for example gender, and there is a missing value, impute the missing value with the most frequent one. So like more like the mode. So if most of them are males, then there is a high probability the missing one will be a male. And if it is female, whatever impute it with the mode. We can specify more than one. We can also say that okay, after that, we can also impute with the mean, we can also impute with the median. We can do more than median and all those ones. But let's just keep the two. Let's just keep the one rather two, so that I don't confuse you. So the next thing I'm going to do, this thing is to set a this thing for the ordinal encoder. And here I realized that when I use single quotes, it was giving me problems. So always advise you use double quotes. So also first you set the ordinal the name of the stage. So you can see that we have simple imputer. So if you want to set a parameter of a simple imputer, you first call the parameter name. So simple imputer, is it simple imputer underscore underscore. Then what in simple imputer do you want to set? The strategy. So the same way, ordinal encoder underscore underscore, meaning in the ordinal encoder we have handle unknown. And this is telling Python, like, if you see something you don't know, for example, in the gender, we have male and female, but maybe we can give you a data, or somebody can, let's say it is in production, there, it is in action. We have a model there, like ChatGPT, for instance, and we ask the person gender, then he says trans. The model wasn't trained on trans. You get it, so he may not understand it. But we're saying that don't stop this thing. If you see something you don't know, then what you have to do is go into your listing, and then you have to use um, the encoded value. So more like we have like a stock of encoders there. So go into that, search in there, and then just encode it. So or more like use the ones you know. So maybe put it in male or female. If you see that he is more male, put him in male. If it is more female, put the person in more female. So we do the same for um we also saying that when you are also encoding and you see an unknown value, something you don't know, now represent it with 30,000. It is something in Python, just represent it with. I didn't want it to. I didn't want to more like put it put a value which was kind of close to it. So I put a very strange value so that it doesn't have an effect on it, because we know our data doesn't have much of this. And then we have the random forest classifier. We have the maximum, the max depth, depth or depth. The depth is telling how many stages do you want to go. How many stages. Now I was given a scenario of finding the factors of 32, where you do 2 times 16, you see it. So how many stages, the depth, how many stages do you want it to go? We don't know, but we setting that pick first 10 stages, you can go, then you count. So we want you to be given a range from 10 to 50, and the incremental step is actually 10. So what we say is that when you pick 10, and then you train, look at it, is it a good model? Then you increase the value by 10. So now you go to 20, then you pick 20, you pick 30, then you pick 40, something like that. Then the same thing, the number of estimators is also, the n estimators is actually um, a parameter in a hyperparameter in um, random forest classifier, which is talking of how many submodels. I was talking of random forest classifier is a collection of models put together, decision trees. So how many decision trees do you want to keep? So I'm saying that since we don't know, we want to iterate to pick the best combination. We start from 25 models and then so pick between 25 and 100. So kind of like iterate through to see which one is best. And then the incremental step is 25. So more like if you start from 25, next one increase it by 25, so 25 to 25. So from 25 we go to 30, you go to 75. Now, and if I run this, you can see that, yeah, it is a dictionary here. Now, when we come here, now we have that we want our model, so we're going to fit our model, which is going to be in a grid search. So the grid search is telling Python that, you see, I have these guys in here. So I want you to fit the model by iterating through all these guys in here, doing more like combination and permutation and combination. So when you pick, for example, this imputation strategy and then this ordinal encoder strategy and this, combine it with um, um, maximum depth of 10 and then number of 25 and number of estimators and do same by picking maybe 20 by 20 25. Do same by picking 20 by 100, like more like iterations to see which one gives the best performance. And then CV is more like, so it's just like this. Maybe let me, before, let me clean this guy. So I know it's a bit technical, but when you sit down and go over it, you'll be fine. So we use grid search CV, and then always I like to kind of like put them in here like this, yeah. And then we provide the model. The first thing is we provide a model or a pipeline. You provide the pipeline you did, and the pipeline. This is a pipeline we did. We're saving it in a variable called CLF. So we say that, you know what, this is the model we want you to pick. So CLF, which is a pipeline we created. Come on, I don't want any CLF. Yeah. And then the second parameter is called param grade. So param grade is telling us what is the parameter grade search. More like what is the dictionary you've provided. What are the range of things you want me to do the permutations and combinations of. And that is what we did here. And we saved it in a variable called params, short form of parameters. So params. And then another thing is CV. How many iterations do you want me to do? How many repetitions? I want you to go 5 times. You can specify. We know that it is heavy, so it takes a lot of time. And then now n jobs and variables is more like to kind of um, it's more like to kind of suppress and then make it run smooth. So variables is more like telling it, if you set it to one, be more like telling it don't output a lot of rubbish to me. Like there's a lot of things you output if you don't set variables. You want only the good one. So this is what is actually going on here. And we're saving this guy here with in a variable called model. So our new model is actually going to be like more like an iteration with you know um this thing, what do you call it? A grid search. And we have a pipeline which is encoding, imputing first, then ordinal encoder, and then so if we run this, you can see that yes, it is a grid search with these guys in here. And then after it's these are models. So the model is actually a grid search, and it is also having a pipeline in there. And the pipeline has 3 stages. So it is a simple imputer. It will first run simple imputer to impute all missing values, encode them into ordinal encoders, then before you feed it to the random forest classifier model, where it will repeat itself, repetition. So this is a very high level machine learning model. Now after knowing this, now let's train the model on the training data. Now this can take some time, you know. So if you run, it might take some time, to be honest. It depends on your machine. If your machine is the CPUs are not that strong, or if you don't have GPUs, it might take maybe some few minutes, right? Some can even take an hour or something like that. So you can see that it is fitting five foods, so five iterations, and each of them has 12 candidates. More like because of the combination, it is doing 12 combinations. So five times, so each one round it does train more like it does 12 iterations. So 5 times 12 is going to actually run, or it's going to do 60 iterations, which is going to, so more like because of permutation and combination, it has we go in 5 rounds, but in each round it will do 12 combinations. So in all, after the 5 rounds, it had trained 60 models. So we can see that we've successfully trained it. Now let's look at the training um, accuracy. So before, the logistic regression model had a training accuracy of 95.42. Now let's look at this. This guy has woo, a training accuracy of 96.89. Let's say 89, yeah. So it is way, way ahead. We can see that it is beating our baseline. This thing model is really performing well. And one thing you have to know is when you start, when you run a model, the training accuracy it can differ. You can see that here when I first did it, the training accuracy was even 97.3 um, 0, or let's say zero point 0.3, but now it is 96. It can go up depending. The thing is, my CPU right now, my CPU is in use. I am filming, I am teaching, I am doing other stuff here, and I'm also training the system. That is why. So if you are not doing anything on the machine, or maybe you have GPUs, it would improve the performance, even maybe to 98% or 99. So don't worry so much about it. If you don't have a good machine learning, sometimes it can take you days for you to. So now let's look at. We made some predictions, and you can see that now these guys, yeah, yes. And then let's make first 20 predictions, and let's check the testing accuracy. So now when we check it, boom, we have 100%. Before we had around 94 point something. Now because of the high level programming, machine learning techniques we did, it is able to learn very, very well that we have 100% training, you know, accuracy, which is so splendid. But don't be so much happy. I've never seen, I have not used 100%, although it's still not 100%. I'll do something about it in real life. But it is very good to get a very splendid, superb percent, um, validation percent. And always don't forget that the validation or the testing, accuracy should always be higher than the the training accuracy. So 100%, which is higher than 96 point system, which is a good thing. The other way around suggests that it is overfitting. Now let's do the confusion matrix display on the training listing to see. So now we can see that now the data has, or the training data, it actually predicted 4,522 of them to be, no, and then it was actually right. And we had 77 patients who actually had stroke. But our model was able to correctly predict them to be, all of them. So you can see it never did any mistake on the no patients and then the yes patients as well. So it did a splendid job. Then let's look at on the test data too. So on the test data, we have 508 no's, which were always right, and three patients were actually having stroke, and it was able to identify them all, which is very, very splendid. So this is a high level this thing. It's so awesome. We've built a very robust machine learning model. Trust me, this is what we are doing out there for the money we take it. Yeah. I don't know why I'm even teaching you guys this. It's too high for you guys, but I think it's an eye opener. Yeah. And I'm very sure you guys are enjoying it. So now let's look at how to deploy the model. So now with Gradio, we always deploy it with Gradio, and this is going to be very, very simple. So I import Gradio, and then always if you want to um, deploy a model in Gradio, you have to first wrap the model in a function. So more like you have to create a function which will allow the user to input the um, the inputs. I mean your age, gender, and those things, and then you have to know how to feed it into the model. So this function is actually called predictor. So it is taking the gender and always make sure that the parameters here are the same as the parameters you use to train the model. So we have that is why I call the gender. So we have gender, we have smoking age, blah 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 blah. So when we do that, we have gender here. So we provide gender, age, blah blah, and then we convert it into a data frame. And then when we convert it into a data frame, we actually use it. We predict the model predicts. Um, so you can see here we do model dot predict prover. So predicts the probability, and then we return that. So this is a function too, but this is the radio function too. So radio has something very simple. So we do gr.interface. Now the title is to give it, this splendid title here. So stroke, I'm calling it stroke prediction app, and then it takes three things. Fn, which is the function. So the function you created. So it is called Fn is equal to predictor. The function I created up here, I call it predictor. You can call it any way. I don't know why I call it predictor. Maybe I was just, I don't know. Then it takes the input. So the input is a list of what it is taking. So in the order of how the function is so gender. What is gender? Don't come and put gender there. But gender is a text, whether it is male or female. So gender, it is a text. So it's a string. So you text. Then age is a number. In that order. Hypertension is either 1 or 0. So it's a number. Then we have heart disease, which is, do you have heart disease? You provide 1 for yes, 0 for no. So saying that this is also going to be a number, and we do same for the rest. Now the output is going to be a number. That is your probability of getting stroke. And then after doing that, you do app.launch to launch the app. So if I run this, it takes some time. I hope it works because I didn't really check the model. So this is it, and you can see that you have a link here. Where you click on it, you have the app, open in a new browser for you where you can run it. Or if you want, you can just do here. When you do the app dot launch, you can do that. You can specify share is equal to true, and if you do that, it's going to give you an external link on radio so that you can host it there and run. So if you do share is equal to true, you see it is kind of running on my listing, which is not a good thing. Um, my machine isn't that good. I bent it few time ago, so I'm not going to try it again. Let me interrupt. Don't do that. Yes. So you can try it on your machine. I'm not going to set it to true. I'm just going to launch it. So you can launch it and try it. So dude or guys, sorry, guys, that's how we train. So let me see. This is here. So gender, I can see. So always make sure that it matches what. So I can see that I'm a male and the age. We provide my age. Why do you want to know my age? So I am 23 and no, I don't have hypertension. Jeez. Heart disease, no. Marriage status, no. I'm not married. I'm single. Work type, I work private company, and the residential status, I'm in the city. Kumasi. Average glucose level. Let me just type it in. I don't know what that is. BMI, I don't also know what that is. Let me give you another number. Smoking status, never smoked, and I just click submit. I have an error. I know why. I didn't really take time to do this thing. So you can do more to it. It's coming from here, the input and output. I didn't really do much time. I didn't have much time in there. So if you want to know why, it is this. So maybe let me. So if you do model dot predict prover, and maybe you give say x text, you see it will give you kind of like an array. So these are the probabilities, the second column. So if you want to select that, then you have to do this, something like this. Say that I want all the rows with the second column, and it's going to give you the actual this thing. So that is why the model is having a this thing. So when you come here, it should actually be model of predict prover, and then you do this thing, you add this thing to it. So I hope it works. So let's run it and see. Whew. Let's finish. So let me use this guy. Yeah, I'm not going to use myself. Let me use this guy. So this guy is a male, and his age is 67, and he has no hypertension. He has heart disease, and yeah, he's married before, and his work type is private, like mine. Mind you, make sure you type just like they are here. He stays in the city, so you can see the private has capital P. That is one downside of the traditional machine learning, where deep learning comes in. Now BMI, he has 36.6, so 36.6, and then smoking status, formerly smoked. This guy is a ganja, it's a Rastafarian. And so let's submit and see. So okay, now you can see his probability of stroke is actually probability of getting stroke is actually 0.62, so which is like 62%. So let's go and format this up here. It's becoming interesting, right? I know I'm using over time, but please let me. Pardon me to use that. So let's round this. Let's round it to two, maybe two decimal places. Yeah, we want to round it. It shouldn't be that weird. Like, so maybe you can trade it and then use your actual data, whether you are. So this guy is boom again 67, and you can use these up and down arrows to navigate it. So this one to this one yes, and yeah, this is a yes, capital Y. Web type is private with capital P. Residential type is urban. Or how do we mention it? Urban. Me, um, I'm a boomer. I'm not a Gen Z. So I say urban, right? But Sandra will say urban. Smoking status, only smoked. Let's submit. Error. Oh, maybe it's from here. Yeah, I'm very sure. So we cannot probably. Um, you can look into that. Maybe we can, instead of doing it, we have to do it from here before we. Maybe you have to wrap it. I don't want to take much of your time. Yeah, so this is the actual listing of it. But to solve that, you can just I think you can just do round in here. You want to round this maybe to two decimal place, and you are good to go. It should work. Yeah. So, guys, that's it. I think it's been very awesome. Let me take your questions. I've squeezed you today full 2 hours. Let me take your questions and then we call it today. Any questions? Can allow more, you can go ahead.
Uh-huh. Please, I would like to ask that. You see, the previous one we were working with, the one we encoded,
Yeah.
we used, I think, a certain linear, logistic regression, sorry,
Mm-hmm.
to predict the stroke A. But we are having is it one, we didn't have any predicted A for those people who actually had the stroke. It was, I think, zero. So does that mean it's a bad model, or so did we actually reject the model to, I mean, go ahead to do this one, or it's still there?
Mm-hmm.
Because I'm confused.
So the
And
whole thing, okay.
you see, we also started with the first one. We also started with, you see, from the start, we also started with I think this random forest, yeah, to classify, to help with the classification something. Yeah, I was confused with that part, and then we just, after the classification, we just walked into the logistic regression. It's
I
like
don't
I'm
get
I'm confused.
I
So
don't
is
get
that
you.
I want to ask that the logistic regression, are we rejecting it because it's a bad stroke? Yeah. So are we rejecting it because it's a bad model, or we are
No.
accepting it? Because I don't understand.
Okay. So take it like this. You are learning now. So I am trying to show you all the tricks in there. So when we use the logistic regression, you could see that the model wasn't performing as better as using um, the random forest classifier, and I gave reasons why. I was like, probably, and it wasn't. It's not even probably. Obviously, the model doesn't. The independent variables and the independent variable do not have linear relationship. So you could see that. Let me try scroll up there to the where we did it. Where is the yeah? You can see that they are almost faint, right? So this is true. The dependent variable. You can see that it doesn't really have strong correlation with any of them. So when we built the logistic regression, we saw that the performance wasn't really well. There is a way to improve it, but even if you improve, it wouldn't be as robust as using the the non-linear model like random forest or probably XGBoost or something like that. Why? Because there isn't so much linear relationships between the independent variable and the dependent variable. And we got to know that through the correlation. There are other ways to do. Now it is up to you, but it is, this is stroke, this is disease. Imagine you have a model which a hospital is using, and it is not as robust as what maybe probably we are having right now with the random forest classifier. People, you're always going to kill people because you go and tell somebody, oh, you don't have a stroke, maybe the person has a stroke, or maybe hey, you have a stroke, meanwhile the person doesn't have a stroke, and start thinking it's more like building an ace, a classifier to classify whether someone has ace or not. And you go and they test and they say you have ace. Meanwhile, you don't have it. It can kill you for the rest of your distance, right? So you always look into building a model which is more robust. We can maybe balance the data. That is what we will look into at our next meeting. When we balance the data, you can see that it will help us probably improve the performance of the logistic regression. But the bottom line is sometimes the data you have may not be fit for that particular machine learning algorithm. That is why we don't have just one algorithm. We have linear ones, non-linear ones. So depending on the type of data or the nature of the data or the relationship that exists, then you choose which one to go. So I don't know whether Nanawa you are cool now with that one. And what was the other question you have? Nanawa, are you there? Yeah, you can.
Uh-huh. Okay, yeah, please, I get you. I understand now. Thank you very much. Okay, and please, I also want to ask this. You see, when we were working with the logistic regression, we first encoded, we changed our text and everything to numbers. Yes, but you see, when we came to the random forest, you see, we were able to work. I don't know. I didn't see any encoding like as we did in the logistic regression. I think we were able to work with the text and all that. So I want to ask that for logistic regression and linear regression, is it always that we have to change into numbers, or we also have a technique to, use the same data type, like as in if it's a string or text? Yeah.
Nanawa, tell me you probably got up to go and eat. Or are you hungry? I'm eating.
No.
Probably, yeah. I can sense you're hungry. I'm also very hungry too. So you maybe slept off at that point. I told you guys, so this is a random forest classifier you're talking about. So when I go here, I told you guys that initially I am showing you how to hard code, manually encode the variables. But there is a way to automatically do that, right? So here I am now introducing the automatic way using a pipeline. So I'm saying that I'm building a pipeline which first imputes the missing value. So you can see we not even impute the BMI missing values ourselves. So the missing, it's a pipeline, so more like pipeline with a lot of things happening in there. So the first thing is when the data enters the pipeline, it should impute. In other words, replace all the missing values. And then when it finish imputing, it should encode ordinally, the values. So the encoder or the ordinary encoder function will transform all the non-numeric, features into numeric before it forwards or brings it to the random forest classifier. So that is why we not do. So this is the automatic way. We have other encoding techniques like one hot encoding and then other encoding, categorical encoders and all those stuff. And then for random forest classifier, it works very well, or it is recommended you always use ordinal encoder. We can also create a pipeline for the logistic regression where we're going to use, like, for example, one hot encoding. So something like, um, maybe, let me see. Now, I'm hungry, but let me. So we can make a pipeline. Um, we can make a pipeline like this. And then in the pipeline, we say that, okay, we will first impute the missing values. Fine. When we impute the missing values, the next thing is, instead of this thing, we will use one hot encoding. So we will learn more about one hot encoding too. But if you are curious, our advice, I always encourage, go in there. You know. So now after that, we use logistic regression, probably set the maximum iter to maybe say 1,000. And this is also another pipeline. So if I'm doing this, there is no need I go there and manually encode gender to those things. So when I feed the data in straight here, it will first impute, and then it would encode. This layer is encoding it. So what I would have done manually, I want to do it automatically. Then feed it to the logistic regression, and I'm good to go. Now, are you okay?
Yes, please. I think I didn't hear it well from there. Yeah, thank you very much.
Yeah, probably you were yawning. Comedy. So guys, any other question? Sandra. Ask your questions. Like, ask.
I think after going through, I'll have questions. It's a whole lot though. We'll manage.
I hope you are not sleeping,
No, I'm not sleeping.
and I hope you are not having a week. It's a lot, I understand. Don't worry, you'll be fine. Like, trust me.
Yeah, exactly.
Yeah. Fauzan, any question? Rashad, Abubakar Siddiq, any questions? So if you don't have any questions, guys, let me stop recording here.